If you don't think about it too carefully, it appears to be a very simple problem. Hey, you need to find some relative extrema? You just look for where the derivative is 0, problem solved. No, it is not so simple. So let us consider this a little bit more carefully. What I want you to do right now is take 3 or 4 minutes and come up with some examples. Don't blurt them out either. Just like think quietly and then share quietly with the people around you. I want a function which has a derivative of 0 at a certain place, yet that spot is not a relative maximum or relative minimum. This is what you were saying already. And I want another example of a function which has a relative max or relative min somewhere, but the derivative is not 0 there. Go. I'll write all that out more carefully, but start like this.
Wait, no. No, yeah, because it doesn't have
Does that count as
it has a value, but it does not.
That's fine. This is supposed to be like the X. Wait, I can see like absolute value of X. You draw an X. I'm doing bad times.
Well, it could just not have
It doesn't actually have 0. Have a point where it's 0? Yeah, the middle. Yeah, but is it actually 0? Yeah. Huh. Okay. Oh, yeah, of course. Okay, yeah. And then like absolute value yeah.
Kevin, are you trying to like create like micro cards and like
It's like this. I am written.
what am I doing? What are you doing? What are we all doing?
I'm not one of those like you can play with your laptop type teachers. All right, good. What do you got? Give me a function where the derivative is 0, but there's no relative min or max there. Everyone. Woo! That is the classic example. We kind of already talked about this a little bit when we talked about like what is a horizontal what is an asymptote day a little bit. This came up, right? But yes, you are exactly correct. If you take the function f of x equals x cubed, it is definitely true that the derivative is 0 at x equals 0. If you don't believe me, I can differentiate. It's 3x squared. Damn, there it is. F prime of 0 is 0. But it is certainly not a max, right? So therefore, it's more complicated than just if the derivative is 0, there's a relative min or max. Does everyone feel this deep in their hearts? Yes. Good. It is also like double complicated because the converse isn't true either. Give me an example of a function that has a relative min or max at a certain absolute value. Good. That has absolute value. And notice that this is a little bit of a trick, right? Because yes, this is a relative minimum because it's smaller than all the points nearby, but the derivative is not 0 there for the sort of technicality reason that there is no derivative there. Follow? Agree? Because f prime of 0 does not exist. Okay, so does anyone want to sort of make a claim that they think is probably true now regarding the sort of trickiness of this counterexample?
It's a piecewise function.
Yeah.
If the derivative exists, then it's when it's either that.
Yeah, he says basically the only way you're going to be able to come up with an example of a place where a function is a min or max, but the derivative is not 0 there, is if the derivative doesn't exist there at all. Okay, that was like some weird triple negative. So the way to say it more cleanly goes under the name of Fermat's theorem.
I've heard that.
I don't know why everyone's groaning. And from what Fermat's theorem, this isn't in the book, but I think it's important. says, if a function has a relative min or max at a certain point, and the derivative exists there, then the derivative must be 0. Cool? Okay, so let's write that down. If f has a, I'm just going to say relative max, but it holds for the min also. If f has a relative max at x equals c, and f prime of c exists, then f prime of c is 0. Do you kind of believe it, ish?
Yeah.
I believe it. All right, good. We are going to prove this right now. And this proof is, I don't know how to say that. I don't mean this to sound insulting, but this proof is easy, but it's going to be hard for you. Because it's one of these proofs where, like, you just have to have some experience in doing proofs like this. It's very short, and it doesn't involve a lot of, like, deep math or anything, but it does involve you, like, writing out the precise definitions of every little thing that you're trying to do, and then suddenly you just blink and it's done. Okay, so here we go. First of all, this is like how to be a mathematician, like 101, whatever. Note that this theorem is a conditional. It says if some stuff, then some stuff, yeah? Okay, so whenever you have to prove an if-then statement, you should assume the antecedent and try to derive the consequence. So what we are going to do right now is we are going to assume that f has a relative max at x equals c, and we're going to assume that f prime of c exists. And somehow, merely from those two assumptions, we are going to conclude that the derivative is 0. Okay. Well, how are we going to, like, use these two sort of facts somehow? What does it even mean to say that f has a relative max at x equals c? Svetlana is pointing to the board, which has now been erased, in which there was a definition. So, what is the definition of f has a relative max at x equals c? Well, the definition is just like basically f of c is the biggest nearby, right? So that's kind of what one is saying, right? F of c is largest y value nearby. Okay, and so I'll put a box around this because that's like a math fact that I have access to or something. And what does it mean to say that f prime of c exists?
The limit exists there.
Yes, Bracklin says this feels like one of those math proofs where I'm going to have to like use the actual definition of the derivative as a limit. And so if I know the derivative exists, the derivative is a limit. So what I can say for sure is that the limit as x approaches c of f of x minus f of c over x minus c exists. Those are the two things I know. And I haven't done anything yet. I'm just listing all of my like supplies or whatever. Okay, and what is it that I need to prove?
That like f of c is 0. Well, the
That
limit
the derivative is 0.
Yeah.
In other words, a couple people are realizing that ultimately this boils down to showing that a particular limit is 0, right? So what we need to do is we need to show that the limit as x approaches c of f of x minus f of c over x minus c is 0. If I can show that that's 0, I've proved the theorem. Alright, do you see what I mean by just breaking it down into tiny little pieces, and then it becomes like not that much to do. Alright, why should this limit be 0? Just look at the numerator and denominator and see if you notice anything. Yeah.
I like sort of like f of c is like, oh, f of c is always bigger than or equal to f of x.
Wait, no. Yeah.
F of C is almost bigger than that.
Yeah.
Yeah, they're equal. Because it's like,
And on one side, x is getting bigger, so it's going to be like both positive and negative. And it exists, so it has to be approaching a value. And if it's approaching like a positive value from one side and a negative value from another side, it's going to be going to 0, because that's like the only place where it can be positive on one side and negative on the other.
Exactly.
Yeah, Bracken just mumbled out the whole proof, which is, what she said is, if you just start looking at the numerator and denominator, just like notice some crap. Justin said it already, right? Somehow the fact that f of c is the biggest, what does that tell me about my numerator?
It's negative.
Guaranteed to be negative, or 0. Does everyone feel that? Right? This numerator's got to be negative or 0 because f of c is bigger than everything else. What about the denominator?
Positive or negative.
It's positive or negative depending on what side of c we're on. That suggests that we should consider the limit as x approaches c from the left of f of x minus f of c over x minus c. And we should consider the limit as x approaches c from the right of f of x minus f of c over x minus c. Taking these one at a time, let's just now sort of conclude what we sort of just mentioned, right? Since f of c is the relative max, then it means that this top thing is going to be something which is less than or equal to 0. Everyone agree? The numerator must be less than or equal to 0 because f of x is always less than or equal to f of c. And what can I say about the denominator? If x is if we're approaching c from the left, then x is a little bit less than c. So this is guaranteed to be negative. This is something negative. Okay, well, if you divide something less than or equal to 0 by something less than 0, what do you get?
0 or positive.
Something which is
0 or bigger.
0 or bigger, right? So the answer is something greater than or equal to 0.
So like, how do you write this out formally?
That's pretty formal.
What are you talking about?
So, I mean, I just could use letters instead, you know, but
That's it.
call it L, where L is less than or equal to 0. Okay, and what can I say about the numerator now?
It's also something that's less than or equal to 0.
It is still something less than or equal to 0. But now the denominator, if I'm approaching c from the right,
Something positive. Greater than 0.
it's got to be something greater than 0. So we're sort of like performing a careful case analysis on the numerator and denominator, both limit from the left and limit from the right.
Oh, and then
What happens if you divide something which is less than or equal to 0 by something which is greater than 0?
Something less than or equal to
What you get is something which is less than or equal to 0. But now we use our crucial fact, which is
it has
to exist.
that this limit exists. Since this limit exists, the left-hand limit must equal the right-hand limit. So these two have to be the same. Well, I only know one number which is greater than or equal to 0 and less than or equal to 0. That number is 0. Therefore, this limit is 0. Follow?
Yeah.
Okay, good. Fermat's theorem is great because what it tells me is that there are two different places we should look for relative extrema. Here, oh, this is going to be good. I've never drawn this before. This is a brilliant idea. Watch this. Okay, so here's a function, and I want to know everything there is to know about this function. Notice that if I search for all the places where the derivative is 0, does that give me a relative min or max necessarily?
No.
Not necessarily. But when searching for all the places where the derivative is 0, I will eventually, according to Fermat's theorem, find all the minima and maxima. Do you follow this? It's like a converse thing, right? Just because the derivative is 0 doesn't mean it's a relative min or max. But if the derivative exists and it's a relative min or max, then it will be 0.
Yeah.
In other words, I can find all the relative minima and maxima by looking for all the places where the derivative is 0. And what other points do I have to worry about if I'm looking for minima and maxima? Places where the derivative does not exist. So the strategy should be as follows. Search for all the places where the derivative is 0. 1, 2. Search for all the places where the derivative does not exist. Boom. And then check them all to see if they are actually relative extrema.
And endpoints?
This is the method for finding relative extrema. And Svetlana says, if you check the endpoints and you also find all the relative extrema, then you've just found all the extrema, man. Get it?
Yeah.
Okay, good. Good thing there's a half an hour left in class so we can do 3 long examples. Let's go. Standard Rose joke never gets old.
Never.
Good. So, let's do a problem. Here we go. I might just continue this into 5th period and make you guys watch like a 5-minute video, or make it optional swing on it. All right, let's go. Here I have 3 functions for you: x cubed minus 3x squared plus 1, and we are going to look for this on the interval -1/2 4.
He's been in the hand of Greek people again. I hate you.
Okay. Oh, goal. I should say what the goal is. The goal is find the minimum and maximum. Cool. Find the absolute minimum and maximum of f on this interval. Okay. What should we do first, just to get it out of the way to make sure that we don't forget?
Endpoints.
Endpoints. Let's check the endpoints because the absolute maximum and minimum might be the endpoints, yeah? So checking endpoints is a very important part of the algorithm. Okay, so plug in -1/2 into this function and tell me what you get. And plug in 4, everyone do that right now. I do it the fancy way, because I'm a fancy person. Wait, can I even do this way? Did you get 1/8? Yep. Woo! I don't know if that was any faster.
That's what I got.
Boom. Okay, so step 1. F of -1/2 is 1/8, and f of 17. What? F of 4 is 17. Alright, so those are important facts. Now, I need to go searching for all the relative extrema. Cool? So where should I search for relative extrema? We should find where the derivative is 0 and where the derivative does not exist. Oh, by the way, there's a name for that entire category of points. They are called critical points, or our book calls them critical values. So critical values are places where the derivative is 0 or does not exist. Okay, this is a polynomial, so the derivative is going to exist everywhere. So we merely have to search for where the derivative is 0. Let's do it. Take the derivative. What do you get?
3x squared minus 6x.
Woo! 3x squared minus 6x. When is that derivative 0?
When x equals 0.
That's one of them.
And wait, what? 3x minus 6, so x equals 2.
Woo! Good. So, what we now know is that we have critical values 0 and 2. Okay, now I want to be very clear about the logic here. I am not sure yet whether these are relative maxima or minima. You feel that? I want you to feel it. We don't quite know yet. And in fact, that's going to be a whole nother day where we're going to determine precisely how to be sure. Although it's not a big mystery, but we're not going to settle this issue right now. But it is sufficient if your goal is to just find the absolute maximum, maximum minimum, at absolute minimum. It is sufficient to just try all these points. Because, well, first let's just do them. What is f of 0? 1, and f of 2 is -3. My paper says -3. Okay, so here's what I got. I got 4 y values. Okay, I think this logic is kind of subtle, so I'm going to say this very carefully. Not sure whether these are relative maxima or minima, but it doesn't exactly matter just right now, because where must the absolute maximum or minima exist if it's a continuous function?
One of these values.
It has to be either, remember, if you give me a continuous function on a closed interval, the only possible locations for the maximum or minimum are the endpoints or at a relative maximum or minimum. So leaving open whether or not these actually are relative maxima or minima, if I just test them all, then like I will stumble upon the maximum or minimum like by following this algorithm. Is that clear?
Yeah.
Like if the goal is to find the maximum and minimum, then I can just check the endpoints and all the maybe relative maxima or minima, and like the maximum or minimum will appear among that list of checked points. Follow?
Yeah.
Okay, I'm ready to state my conclusion. The conclusion of this problem is that the max of f on the interval -1/2, 4 is
17.
17. Good. And you just listed as a y value. In this case, it turned out to be the right endpoint. And the minimum of f on the interval -1/2, 4 is -3. So in this case, the minimum turned out to be what is surely a relative minimum. Follow? And actually, I could probably just pretty much guess about what this function looks like now, right? I know its y-intercept is 0. I know that at -1/2, it's like -1/8. What else do I know? At 2, it's -3. So it must do a kind of a this type thing. And then I know that by the time I get to 4, it's like way up high here. So this function must, something went wrong. No, I forgot something. F of 0 is 1, yeah. So this is probably a relative maximum, though I'm not positive. What were you saying? -1/2. It is positive 1/8. That's a fact. How did I get that wrong? Just dumb.
-4.
-4.
Good? It's a classic -1 situation. Good. Connor, good? Okay, good. All right, what do we have? How many minutes do we have left?
2.
Good, perfect.
20.
Let's do another problem. f of x equals x minus 2 sine x on the interval 0 to pi. Go. No, you have 4 whole minutes.
Oh, so it's 40.
Wait, 4 whole minutes?
Make it 40.
Alright, when the bell rings, just quietly leave, don't mess up my video. I'm going to do this problem to completion. You could like watch it or not. I think you guys got the big picture. Cool?
Oh, they're both 0.
Good. Homework due Monday, Tuesday, on
Thursday.
test on Thursday. Single 45-minute test on Thursday. Homework due Tuesday on this stuff and this packet that I passed out. I think I'm going to give you guys a take-home quiz next week too. Get some more points on this quarter.
Oh, yeah. Oh, I didn't do the very first one. That was in
What did you think last class?
Last class like the test day? Okay, good. What should we do? First we should
Endpoints.
try the endpoints. F of 0 is 0, that was easy. F of 2 pi is just 2 pi. So that's like about 6.28. Alright, now I should go searching for relative extrema, so I should find out everywhere where the derivative is 0. So that means taking the derivative, yeah?
Yeah.
So that's 1 minus 2 cosine x, true?
Yeah.
Alright, set that equal to 0. That's going to happen whenever cosine x is
1/2.
1/2, which happens.
Pi over 3.
That's so wrong.
Pi over 4 and like
Oh my
pi over
God.
3. Pi over 3.
Very good at trade.
These are like basic things that you need to be like correct on 100% of the time. All right, good. Therefore, I will now check these. Wait, actually, we're actually going to finish this problem. Maybe. So let's check these. If you plug in pi over 3, what do you get? What is sine of pi over 3?
Like 1/2.
And that's wrong again. Sometimes I feel like you can't be like real. Sine of root 3 over 2 is, sine of pi over 3 is root 3 over 2, yeah?
Yeah.
Alright, so this is like pi over 3 minus root 3. Let's call pi over 3 like 1-ish, because it's pretty much like 1, yeah? So this is like 1, and that's like about 1.7, so this is like approximately negative 0.7. That's like not too bad. Good, what if you plug in 5 pi over 3, what do you get? You get 5 pi over 3 minus 2 times, what is the sine of 5 pi over 3? Negative root 3 over 2, right? Yeah. So then that becomes like 5, let's call that basically like 5-ish. Right? Well, it's 5 pi over 3 plus root 3, but now that's like about 6.7, agreed? Because like 5 pi is more or less like 5-ish. Ish. So therefore, what is the max of f on the interval 0 to pi? The answer is 5 pi over 3 plus root 3. And what is the min of f on the interval 0 to pi? Pi over 3 minus root 3. Good. All right, we pretty much finished. The only other thing I was going to say is, I'm just going to leave this running. I'm just going to talk as if no one's paying attention. Is it still focused on this? So like, we once upon a time tried to graph functions like this, and like we couldn't really do it because we didn't know calculus. So recall that this is not an unreasonable function that I may have given you in like pre-calc C or something to graph. How might we have done this? We would have noted that sine x is between -1 and 1. So negative sine x would also be between -1 and 1. So negative 2 sine x would be between negative 2 and 2. And so negative 2 sine x would be between x minus 2 and x plus 2. But by adding x to both sides of it. Right, and so we can say that this function is contained within an envelope of okay, so I shall draw the y equals, yeah. Is that just still recording? Good. I shall draw the y equals x minus 2 envelope and the y equals x plus 2 envelope. And what I know is that my function must live somewhere between these lines. Alright, so then, once upon a time, talking to myself now, we would graph this function by doing some point plotting. So like at 0, it's going to be 0. At pi, which is about 3-ish, it's also going to be just pi. So that point's pi comma pi, because sine of pi is 0. And then if you plug in 2 pi, 3, 4, 5, 6, you get 2 pi. So that's 2 pi comma 2 pi. In other words, whenever you plug in some integer multiple of pi, sine of that will be 0. And so we got like a 0, we got to have, Sujay, remember this? Then the other thing that we did once upon a time was we said, oh yeah, the, what's it called? When will it like hit the top envelope? It will hit the top envelope when sign is as, well actually, or like as big or small as possible, right? So if you plug pi over 2 in here, for example, then you're going to get sine of pi over 2 is 1. So that's pi over 2 minus 2. So that's going to be, and pi over 2 is going to be boom right here. So that point, pi over 2, is going to be where the function hit the bottom of the envelope. Yes, I want a cookie. Hold on, I'm actually recording a video right now. Good. And then where is the function going to hit the top of the envelope? When you plug in 3 pi over 2, because now sine of 3 pi over 2 is negative 1, so that's 2 plus 3 pi over 2. In other words, we're going to land on the y equals x plus 2 upper envelope, and that's going to happen like halfway in between. So that point is 3 pi over 2. This is a bad marker. All right, and then in our pathetic pre-calculus mindset, we could go no further because we couldn't find out where this function is minimum and maximum. But now we can, period 4, even though you've all left the room, it doesn't matter because the math still goes on. We have just learned that the derivative is 0 at pi over 3 and 5 pi over 3. So now if you go over here to pi over 3, which is like about 1-ish, and the answer we got was negative 0.7, I got a point now. And what I can say for sure about that point is there's a horizontal tangent there. And so that point is, I don't even know if anyone can read this, that point is pi over 3, comma, whatever, whereas this point was pi over 2, comma, whatever. And then the other place where things got exciting was at 5 pi over 3, which is where, like something like here-ish, that's also a place we have determined with calculus where there is a horizontal tangent. And now, what we learned about this function is that it must bounce up and down between the envelope, touching the envelope at every like sort of pi over 2, 3 pi over 2, and dropping back onto the line y equals x at every integer multiple of pi. But now my additional information I know is precisely now when this function is minimum. And so that is what this function looks like on the interval 0 to pi. And we could never have previously known where precisely this function was maximum, had a relative maximum minimum. But now with the power of calculus we do know. All right, good. Video's over. Goodbye, all the people. Yeah.